All right, good morning, everyone. So it looks like somebody maybe walked off with the lapel mic, so I can't use it today. So if you have trouble hearing me, just move up to the front. There's plenty of room. Okay, so announcements, homework 4 on Friday. Do pre-lab 1 before your lab 1 starts this week. And then we have the quiz on Wednesday. So the next class is the quiz. Just a reminder, you do not have to come here to write the quiz. Just go wherever you want. You just have to have some kind of device with internet access and a browser that you can go on to Prairie Learn and do the quiz. If you want to write the quiz here, that's fine. I will be here, but you just have to bring a laptop so that you can complete the quiz. I will start the Zoom session the day of the quiz, but it's only going to be for using the chat if you have a question during the quiz. And I'll try to respond relatively quickly. If you do send some message in the chat, don't send it to everybody, just send a direct message to me, and then I'll reply with a direct message to you. Okay, so just before we begin, I thought what I would do is just show you how you would complete the quiz. So let me share this thing. All right. So when you log into Prairie Learn, what you're going to see is something like this. Okay. And so at the bottom is the quiz number 1 link, and that's going to start from Wednesday, January 31st. So if we click it, you'll see something like this. So there's going to be 11 questions, and they're multiple choice questions. So you just click the answer that you want, and then you save that. If at the end of the quiz, you decide, oh, I'm not sure about question 4, I want to go back and change my answer, you can do that. So you can change your answers up until you do the submission. So I'm going to show you what it's going to look like when you start the quiz. And so I just have to go to a view without restrictions here. And so if I was to click on quiz number 1, which you'll do, oh, sorry, let's see, I'm going to log out and log back in. So let's see if that gives you log in. Okay, so go to student view. All right, so you click on quiz number 1. Oh yeah. So, all right. What it will come up with at first is a screen that just says that you have to certify that you are the person that's writing the quiz and you correspond to whoever the person is registered into the class. So it's just kind of an honesty type question. You click that, and then it'll take you into this screen. I'm not going to open a question, but you would open a question and you just start it. When you're done, you just go to the next one and you just go through the quiz. You'll have 40 minutes to complete it and do your submission. Just a reminder, the quiz will be open for a 1-hour window from 10 to 11. And when you start it, there's a 40-minute timer and you have to finish within that 40 minutes. So if you want the full 40 minutes, you must start the quiz by 10:20. If you start it after that, let's say you started at 10:28, then you'll only have 32 minutes to complete the quiz. Okay, any questions about any of that stuff? No. Okay, good. So then let's go back to here. Let's see if I can share my screen. All right, good. And so let's see if I can get this into full screen. All right, so I think we're back in business now. So what we were talking about last time was flux through a closed surface. And so remember, we had this funny notation for our integral where we put a little circle around that integral sign. And that's just there to remind us that we're dealing with a closed surface that doesn't have any holes in it. And so this was one way to calculate the flux. And we went through a series of arguments last class to show that a few different things. One is that the flux phi is going to be proportional to the total charge enclosed by our surface. And so that means if I have a charge sitting outside of the surface, it doesn't contribute any flux at all. It's only the charge that's contained inside that is going to be responsible for the net flux through our closed surface. The second thing we discovered is that if I have a charge Q inside my closed surface, I can move it around to different positions. As long as it stays inside the closed surface, the flux will remain unchanged. Okay. And then the other thing that we learned is that I could also take my closed surface and I could distort its shape. I could stretch it, I could compress it, I could change it from spherical to a cube or to some Cheeto type shape. As long as that charge Q stays inside, the flux doesn't change. So flux is proportional to the charge enclosed, is independent of the position of the charge inside the surface, and is independent of the shape of our surface. Okay, so what that means is if I have these three cases where I have charge Q in a cube, in the center of a cube. In number two, I have charge Q at the corner of a cube, but inside of it. In case three, I have charge Q inside my Cheeto. All of those, if Q is the same in all three of those scenarios, they all have exactly the same flux. Okay, so that's what those 3 points above imply. So what I want to do today is I want to get at Gauss's law. And to do that, what we're going to do is we're going to find a second way to calculate the flux. And it's going to turn out, I've got the results here. This is the result we're working towards today. The second way to calculate the flux will be just taking the total enclosed charge divided by a constant. That's it. And so once we have two ways to calculate the flux, those two ways must give equivalent results. And so they have to be equal to one another. And this thing in the red box here is going to be Gauss's law. And we'll see that that will help us calculate electric fields due to different types of continuous charge distributions. Okay, so how are we going to do that? Well, what we're going to do is we're going to try and just do the calculation. So we're going to find the flux through a closed surface that contains or is containing a point charge Q. Okay. Now, in general, if we wanted to calculate the flux using this integral method that we have, that's potentially a hard calculation. So what we're going to do is we're going to realize that, well, it doesn't matter what the shape of my surface is, and it doesn't matter where the charge is inside that surface, I'll always get the same result. So what I'm going to do is I'm going to make smart choices that will make the calculation easy. And so let's make some statements about what is a good choice and what's a bad choice for the shape of our surface and the position of our point charge. So first, we just note that we're free to pick the shape of the surface and the position of our point charge. And so what we're going to do is we're going to make good choices. We're going to make choices that simplify the calculation. And the calculation we have to do is this integral of E dot dA. Okay, and so what are the simplifying choices? Well, the first thing that we can see is that we have a dot product to evaluate. And the dot product is between the area vector and the electric field. So remember, the way we define the area vector is that we had some area, and then we defined a vector n hat, a unit vector that was perpendicular to that area. And so the dot product is really between n hat and whatever the electric field is. And so the angle between those two. So in general, the dot product between two vectors gives a factor of cosine theta. And cosine theta is easy to deal with in two special cases. One is if the angle is 0, then cosine theta will just be 1. And if the angle is 90 degrees, cosine theta will be 0. So we're going to try to make choices for our surface and the position of the point charge that is going to guarantee that the cosine factor will either be a 1 or a 0. So we either want our electric field to be perpendicular to our surface or parallel to it. Okay, so if E is parallel to dA, then this E dot dA is going to be equal to E dA cosine. And so if they're parallel, the angle between them is 0. And cosine of 0 is going to be 1. And so we just get E dA. So we eliminate the dot product. And in fact, we get rid of all of the vector stuff out of this expression for the flux. Okay. So another possibility is that we choose the electric field to be perpendicular to dA. Then E dot dA will be equal to E dA at cos of 90 degrees. And in some ways, that's even a nicer result because then everything just vanishes and we don't have to worry about those cases. Okay, so there's one more thing for us to consider about the selection of our surface and our point charge position. And that is, if I can make my surface or a part of my surface the same distance away from the charge, charge is the source of electric field. And so if I'm always the same distance away from that charge, the electric field's a constant. Now, if the electric field's a constant, I could take it outside the integral. I could always factor constants outside the integral. And that's another big simplification. So we're going to try to make choices so that when we're at a position on our surface, if we're the same distance away from the point charge, then the electric field at the surface would have to be constant. Yep. Perpendicular. Okay, and so the example that we're going to do is we're going to choose a point charge at the center of a sphere. And so that means no matter where I am on the surface of the sphere, I'm always a distance of the radius away from the point charge. And so at any point on that surface, the electric field has to be exactly the same in magnitude. Okay, so if E has a constant magnitude everywhere on the surface, then we can take the factor E outside the integral. Okay, and so those are the three things that we're going to try to do. And so let's see if we can attack this problem. Okay, so what we're going to do is we're going to choose a spherical surface with Q at the center of the sphere. Okay, so let's draw it. So our surface would be a sphere. And so, okay, we'll try to represent the fact that this is a 3D sphere. And then our charge Q is going to be sitting here at the center, like so. And so there is a distance R between Q and the surface of the sphere. All right, so if I was to draw the electric field due to this point charge, it's going to be radial. And so if it's a positive point charge, it'll be radial and pointing away from Q. And so I'll just draw a few of these lines. Okay, and so here is the electric field. All right, now, if we remember how we defined our unit vectors, our normal unit vectors for our surfaces, if we have a closed surface, we choose those normal vectors to point outwards. And so over here at this point, an outwards pointing normal vector is something like n hat. Here, I'll draw it like that. Okay, and then if I went to some other point, n hat pointing outwards would look like that. And over here, it would look like this. And no matter where I go on the surface, n hat and the electric fields are always parallel. And that was one of the things we said was going to simplify our problem. Okay, so for this geometry, E is always parallel to n hat. And so therefore, this E dot dA is just going to be E dA cosine of 0. And cosine of 0 is 1. And so we just get E dA. So the vector stuff, the dot product is gone. And so now we don't have to worry about that anymore. All right. Now, the other thing we're going to do is we're going to notice that the point charge electric field has a magnitude of KEQ over R squared at the surface of the sphere. Because that distance R is the same between the point charge and any point on the surface of the sphere, this magnitude doesn't change as I move around different locations on my surface. So therefore, E has a constant magnitude everywhere on the surface of the sphere. And so that means we can factor E out of the integral we have to do. All right, so let's then think about this flux calculation. The general expression is E dot dA. But for our particular case, we said E and dA are always parallel. And so the dot product goes away. Okay, and so this is because E is parallel to dA. The next thing we're going to do is we're going to say the electric field's a constant because we chose a smart geometry. So the electric field comes out of the integral. E is constant. Okay, and now let's think about what this remaining bit of the integral really means. It says integrate over the entire surface and add up all the little dAs that contribute to make the full closed surface. So if you add up all the little patches of area, what do you end up getting for our sphere? The total area. What's the surface area of a sphere? 4 pi r squared. Okay, so let's just note that this integral of dA requires us to add up all the little patches of area that make up the entire surface of the sphere. And so that means that this is equal to the surface area of our sphere, and that's equal to 4 pi r squared. Okay, so this complicated looking integral simplifies a lot. Dot product goes away, the electric field comes out, and we're left with just the the integral of dA, and that's just going to be 4 pi r squared. And so all of the problems that we try to do with Gauss's law are going to be of this type. We're always going to look for ways to eliminate the dot product between the electric field and dA, and ways to factor the electric field out of the integral. And that's just going to leave us with taking E and multiplying it by some kind of area of a surface. And that's all it's going to boil down to. Okay, so what we said is our electric field was going to be a constant. And so we said it's going to have this value. So let's label that equation 1. So if we sub in equation 1 for our electric field, we're going to get that phi is equal to Ke Q over r squared times the 4 pi r squared. All right, and so now, beautiful thing happens. The r squareds cancel. And we have 4 pi Ke times Q left over. But remember, Ke we could express as 1 over 4 pi epsilon naught. And so another beautiful thing happens. We're going to cancel these factors of 4 pi. And we're going to be left with phi is equal to, let's see, Q over epsilon naught. Now, this is true for our special case of a point charge at the center of a sphere. But we can move the position of the charge without changing the flux. And so this is also true for a point charge anywhere inside of our closed sphere. We can also change the shape of the sphere. We can make it a Cheeto or a cube or anything you like, as long as it stays a closed surface and the flux doesn't change. And so this result is valid for any charge inside any closed surface at any position inside that closed surface. Okay, so this is valid for any position of Q inside a closed surface of any shape. What people usually do to emphasize that this charge has to be inside the surface is they label this charge Q as Q enclosed. So it means it's enclosed by whatever surface we're thinking about. So to emphasize that Q must be inside the closed surface, we usually add a subscript, Q enclosed. So then phi is equal to, okay, what we started with was this integral. And now what we've shown is that that's also equal to Q enclosed over epsilon naught. And so two expressions for the same quantity, those two expressions must be equal to one another. And so this is our Gauss's law. The integral of E dot dA for a closed surface is Q enclosed over epsilon naught. Gauss's law. All right. So what I want to do is I want to just present a few different scenarios, and I just want us to figure out what the flux is without doing any complicated calculations. Before we do this, let's just think about this for a second. We did this for a point charge, but not all charged objects are point charged. We could take a rod and you could give it some linear charge per unit length, or we could take, you know, some kind of funny like peanut shape and it has a charge on its surface and we put that inside a sphere. Well, if you think about that, if this is true for a point charge, we could put a bunch of point charges, we could line them up in a row, and we can make a line of charge, and this is still going to be valid. So this is also valid not only for point charges, but any distribution of charge that sits inside our closed surface. So since we can form any arbitrary, how do you spell arbitrary? Arbitrary, there's three R's in arbitrary. We can form any arbitrary distribution of charges by assembling a collection of point charges. Gauss's law is valid for any kind of charge distribution. Not just point charges. Okay. So let's do some examples. So the question is, what is the flux through whatever surface I'm going to draw? All right, so let's say I have a spherical surface and I just place Q at some arbitrary position. What's the flux equal to? Yeah. Q over. Yeah, that's right. All we have to do is find the enclosed charge. The enclosed charge here is just Q, and we just divide that enclosed charge by our constant epsilon naught. That's exactly what it is. Okay, so let's start. We'll keep it simple. Let's keep it simple to begin. So here's an approximate cube. And so I just changed the shape of my surface and I put Q over here. What's the flux? Yeah, somebody else. What's the flux in this case? Yeah, it's exactly the same. Okay, and so let's think about some variations. All right. So we'll start with our cube surface again, just because that's one I can draw easily. And so I'm going to put Q over here. What's the flux in this case? 0. There's no enclosed charge. And remember, the idea is that if I have a charge outside of my closed surface, then it's going to have electric field lines that pass through the surface, but every line that enters will also exit. And so there'll be a positive contribution to the flux when it exits the surface. So here we would get phi, like a positive flux on the right-hand surface. And then over here, where the electric field is entering, we would get a negative contribution to the flux, and those two would cancel. But we don't have to think about all those things. Once we're comfortable with this, we would just say phi is 0 since Q enclosed is equal to 0, or Q is outside our closed surface. Okay. I'm going to do 2 more examples. We'll do our Cheeto over here. And so what I'm going to do is I'm going to place a few charges around. We'll put Q1 over here. We'll put Q2 over here, and we'll put Q3 over here. What's the flux equal to? Q1 plus Q2. We're missing one thing. What is it? Epsilon naught. Yeah, that's right. So we only have to think about the charge that's inside. Q enclosed is Q1 and Q2. Q3 is outside. It doesn't count. Yeah. Yep. Yeah, that would be a very hard calculation to do because the electric field lines are going to be exiting the cube at funny angles, and it'll be different angles at all different points on the surface. It would be a really, really hard calculation to do, but if you did it properly, you'd get exactly the same results. Yeah. Yeah. Okay, I've got one more example, and so this one will be a little bit more complicated. I'm going to draw a line of charge. So here's a rod that has some uniform charge distribution. And so this is charge per, here, I'm going to move this so I leave myself a bit of space. The charge per unit length of our rod is lambda, is say Q over L, so whatever that is. Okay, and what I'm going to do is I'm going to put my cube around this rod. Okay, and let's say my cube has sides of, let's say this is length A. And so what I want to know is, here, just to emphasize that this is passing through that thing. Okay, so the question is, what is the flux? Yeah, exactly, that's right. So the only challenge in this problem is to find how much charge is inside this cube. And so whatever the answer is, it's always going to be Q enclosed over epsilon naught. And so Q enclosed is the total charge that's inside the cube. Okay, now what we have inside the cube is a portion of our rod. And our rod has charge per unit length Q over L. So that's like a charge density, a charge per unit length. And so if we know the length of the rod inside the cube, we take lambda times it by that length, that's the total charge that's inside. And so because our cube has length A, the section of the rod inside is also length A, and so lambda times A is the total charge that's inside our cube. Okay, so we need to multiply the charge per unit length of the rod that's by the length of rod that is inside the cube. Okay, that length happens to be, so Q enclosed is equal to lambda times A, and so the flux is equal to Q enclosed, or lambda times A divided by epsilon naught. Right, we could do other tricky things. We could say, well, what if the rod was aligned so that it went like kitty corner? It went from one corner to the kitty corner diagonally across. Well, then all you'd have to do is you'd have to find the length of that diagonal of the cube, and you would take lambda times the length of that diagonal would be Q enclosed divided by epsilon naught. That would be the flux. Okay, good. So what we're gonna do next is we're gonna start perhaps a more interesting problem to try to show the utility of Gauss's law. And so let's see what we can do. Let's use Gauss's law to find the electric field. Electric field due to a uniformly charged sheet. Okay. We wrote down the result before. The result was the charge per unit area divided by 2 times epsilon, I think. We'll find out. So let's see how we're going to tackle this problem. So I'm going to draw a sheet. I can only draw a section of it, but I'm imagining that this sheet is very big. So it extends to, say, plus minus infinity in the X and Y directions. And then we place some charge on this sheet. And the first question I have is, what we're going to try to do is we're going to try to pick a surface. They're usually called Gaussian surfaces that are going to simplify the calculation. So we want the electric field to be either perpendicular to or parallel to whatever surfaces we choose for our Gaussian surface. So in order to do that, we have to know something about the direction of the electric field. So if I was sitting here at point P, somewhere above this surface of charge, right? So let's say I'm above the surface of charge. Oh, it doesn't look very perpendicular, that line, does it? I meant to draw a perpendicular line. So there's point P. What's the direction of the electric field at P going to be? Straight up. Why is it straight up? Yeah, it's positive. Why isn't it like up and to the left or something like that? Yeah, I mean, so a point charge over here would make an electric field that points up and to the right, but one over here is going to make an electric field that points up and to the left, and the left and right components will cancel, and just the upwards components will always add. Okay, so over here, we're going to have the electric field pointing upwards. What about down here? If I had a point Q, I better not use Q. Let's say P1 and let's say P2. What's the electric field direction at P2? Just shout it out. Down, that's right. And so it's for the exact same reason. Electric fields point away from positive charges. So if I'm above the sheet, the electric field is upwards. If I'm below the sheet, the electric field is downwards. Okay. So by symmetry, the electric field anywhere above the sheet is upwards, and it is downwards below the sheet. Whoops, below. Below the sheet. All right. So what I'm going to do is I'm now going to make a choice for the surface we're going to work with. I'm going to draw our sheet again. I won't bother drawing all the charges on it, but let's just remember that this is a charged sheet. And what I'm going to pick for my surface is some arbitrary shape. Well, okay, it's not totally arbitrary, but let me draw it and then we'll talk about it. And then it's also going to go below, and it would have to match that kind of shape. So it would be something like this. All right, so what's arbitrary is the shape of our surface, that the part that's parallel to the sheet. That could be anything. But what it has is a flat top and it has a flat bottom. So we're going to pick our surface such that it has flat top and bottom that are always the same distance from our sheet. Okay, good. Now what I'll do is I'll draw some electric field lines. And so we said the electric field is going to point upwards above the sheet. And so it's pointing upwards. And then like it's pointing upwards at our surface too. So it's always pointing up. And then below the sheet, it's going to be pointing down. So I'll draw some of those as well. All right. And what I'm going to do is I'm going to add some of the normal vectors to our surface. There's kind of three parts of our surface of interest: the top, the bottom, and then the side. Okay, so at the top, the normal vector is perpendicular and pointing outwards. So it's pointing up. And so what we could say is, let me call this n hat top. So I'll call that top. And if we look at that, we say, oh, well, that's interesting. N hat top is exactly parallel to the electric field. So n hat top is parallel to the electric field. So if we had something like E dot dA with the top surface, the top part of our surface, well, they're parallel. So the dot product is going to give us a cosine 0, but we've already written down a bunch of times that cosine of 0 is 1. And so this is going to be E dA top. All right. And then on the bottom, we have n hat bottom. And we can make the exact same kind of arguments. We say, well, n hat bottom is always parallel to the electric field, because below the sheet, the electric field's pointing down. And so the exact same reasoning applies. So the dot product will just go away, and we'll just have a regular product of E times dA, whether it's top or bottom. All right. Now we get something a little more interesting. I'm going to have to try to draw a n hat side. And I'm just going to try to emphasize that these normal vectors are always perpendicular to whatever surface they're attached to. What's the angle between n hat side and the electric field? 90. And it doesn't matter if our side, the portion of the side is above or below the sheet. In both cases, it's a 90-degree angle. So n hat side is perpendicular to the electric field. So E dot dA on the side somewhere is going to be 0. All right, perfect. That's a lot of the hard work. How are we doing time-wise? 4 minutes. Okay, so if we want to calculate the flux, it's E dot dA. Okay, so that's fine. This is an integral over the entire closed surface, but we've already kind of separated our surface into a top part, a bottom part, and a side part. And so this is equivalent to E dot dA for the top plus E dot dA for the bottom plus E dot dA for the side. All right, if I add up all those individual parts of the flux calculation, I've included all of the surfaces of our closed surface. And so this works well. But this is already 0. So we can ignore that last one. Okay, and then we've already said that the two other dot products go away. So this is E dA top plus E dA bottom. Now, we chose our top and bottom surfaces to be flat. And the reason we chose them to be flat is so that everywhere on the top is the same distance from our charged surface. Okay, if we're always the same distance from that source of charge, we would expect the electric field would be everywhere the same at that top surface, and the same goes for the bottom surface. Since the top and bottom surfaces are a constant distance from the sheet, E is constant. All right, so then that means the flux is E times the integral of dA times the top plus E times the integral of dA on the bottom. So we just factored out the oh, what happened? Oh no. So let's see. Screen sharing has ended. Okay. Let's see what happens here. All right, so I'm just going to finish in 1 second here. So if we come back to this picture that we had, and we said that the area of this top surface is, let's just call it area A. And the bottom surface will have the exact same area. Okay, so that means, just like we did for the sphere, the integral of dA over the top surface just means find the total area of the top surface. And so this is just A. And same thing for the bottom surface. And this is 2E times A. So that's the flux. So flux is equal to 2E times A. And the flux is also equal to Q enclosed over epsilon naught. If our surface has charge per unit area, sigma, and we enclose a patch of area A in our surface, then the total enclosed charge is sigma times A. So if, I'm just going to go 1 minute over, I'm almost done. If our sheet has charge per unit area, sigma, then Q enclosed is equal to the charge per unit area times the amount of area that's enclosed in our surface, which is just A. And so that means phi is equal to sigma A over epsilon naught. And these two must be equal. And that requires that 2E times A is equal to sigma A over epsilon naught. And a beautiful thing happens. The factor of the area cancels. And it must cancel because I could have chosen a completely different surface that had a different top area and bottom area. It wouldn't matter because that A is going to cancel. And so E is equal to sigma over 2 epsilon naught. And this is the electric field due to a uniformly charged sheet. All right. Thank you very much. I have office hours today if anyone wants to come see me. Other than that, remember, Wednesday is quiz. You don't have to be here for the quiz.
What's that off the quiz? Like what material?
Oh, it's on the course website. Here, just come here for a second.